Hey there! Tonight we're gently unwrapping one of the universe's most curious questions. It's a question that has puzzled thinkers for centuries, whispered across generations, and quietly guided the hands of countless scientists. Where does space stop? Is it a boundary we can reach, a cosmic wall, or something far more elusive? This journey isn't about finding a simple answer, but about exploring the vast, often surprising landscape of what we think we know about the cosmos. It's a story of patient observation, accidental discoveries, and the profound wonder that follows. So settle in, perhaps with a warm drink, and let your mind drift. If you enjoy these quiet explorations, please consider liking this video and subscribing to the channel. It helps these stories reach more curious minds. Now, let's begin our journey back to a time when the universe began to whisper its oldest secrets. It was the mid-1960s, a time when the universe was just starting to speak to us through new ears. At Bell Labs in Holmdel, New Jersey, two young radio astronomers, Arno Penzias and Robert Wilson, were hard at work. They were using a revolutionary instrument, the Holmdel horn antenna. This massive, elegant structure, shaped like a giant ear, was designed to pick up incredibly faint radio waves, primarily for early satellite communication experiments. Their task was precise: to calibrate the antenna, eliminate all sources of interference, and ensure it could capture the delicate signals from space. They wanted to hear the universe unmarred by earthly static. But a persistent, low-level hiss, a steady static, kept intruding. It was faint, yet unmistakably there, a constant background noise that defied all their attempts to eliminate it. This wasn't the kind of static that came and went. It was uniform, coming from every direction, day and night, regardless of where they pointed the antenna. It was as if the entire sky was humming a quiet, unyielding tune. Their first thought, naturally, was terrestrial interference. They meticulously checked every piece of equipment, every cable, every connection. They even considered something rather mundane: pigeon droppings. Pigeons had nested inside the horn, leaving behind a layer of what's called white dielectric material. Could this be absorbing and re-emitting microwave radiation, causing the noise? It seemed plausible enough to warrant a full clean-out. They painstakingly removed all the droppings, cleaned the entire interior of the antenna, and sealed up the nesting spots. They were confident this would solve the problem, but when they switched the system back on, the hiss was still there, just as strong as before. Frustration mounted. They checked their receivers, their amplifiers, their cooling systems. Every component was scrutinized for any internal noise, any subtle malfunction that might be generating this persistent signal. They even considered the very structure of the antenna itself, its materials, and the surrounding environment. Was it the atmosphere? Terrestrial radio signals? Nothing seemed to fit the uniform, pervasive nature of the noise. They calculated and recalculated, trying to account for every known source of microwave radiation. The sun, distant galaxies, even the Earth's own atmosphere — none of these could explain a signal that was so consistently present from every direction at a constant temperature. It was an enigma. The noise was too uniform, too pervasive to be local. It had to be cosmic. But what in the cosmos could produce such a steady, omnipresent hum? Meanwhile, an hour's drive away, at Princeton University, a group of theoretical physicists led by Robert Dicke were working on a very different problem, one that unknowingly held the key to Penzias and Wilson's mystery. Dicke's team, including Jim Peebles, Dave Roll, and David Wilkinson, were exploring the implications of the Big Bang Theory. Specifically, they were pondering what the universe would have looked like in its earliest moments. Their calculations suggested that if the universe truly began in a hot, dense state, there should be a faint afterglow, a residual radiation permeating all of space. A relic of creation, cooled by billions of years of expansion, now detectable as microwaves. They were even building their own antenna on the rooftop of their physics building, hoping to detect this theoretical cosmic background radiation. They were looking for precisely what Penzias and Wilson were trying to get rid of. The connection came through a chance phone call. Penzias, frustrated by the unexplained noise, mentioned their findings to a colleague who suggested he speak with Dick at Princeton. The conversation must have been electrifying. As Penzias described the persistent, uniform static, Dick's team immediately recognized it. It was exactly what their theory predicted. The noise was not interference, it was the echo of the universe's birth. This accidental discovery, the persistent hiss in their antenna, was the cosmic microwave background, or CMB. It was the faint, ancient light from the universe released when it was only about 380,000 years old, cooled and stretched by expansion into microwaves. It was the oldest light we could ever hope to see, a direct snapshot of the Big Bang's afterglow. This wasn't just a discovery, it was a profound confirmation of how our universe began, a whisper from the very fabric of creation. Penzias and Wilson, initially frustrated by a nuisance, had stumbled upon one of the most significant pieces of evidence for the Big Bang. Their noise became the universe's oldest song, telling us about its fiery beginnings. This first glimmer, the gentle hum of the CMB, painted our universe as a place that began from a single point, expanding ever since. But even as it answered one grand question, it quietly opened the door to countless others. If the universe began, where does its expansion lead? And where, if anywhere, does space truly stop? We'll begin to explore those questions next time. The quiet hum of the cosmic microwave background, that ancient echo, painted a clear picture of our universe's beginning. It confirmed a fiery, dense origin, a moment of creation. But even as this fundamental question found an answer, another, equally profound, began to emerge. If the universe began, where does its expansion lead? And where, if anywhere, does space truly stop? This wasn't a question of physical walls, but one of perception, of what our senses, even aided by the most powerful instruments, could ever hope to grasp. To understand the universe's extent, scientists in the early 20th century had to grapple with a fundamental truth about light itself. For centuries, light was thought to travel instantaneously. But careful measurements and then Einstein's groundbreaking theories revealed something vital. Light has a finite speed. It is incredibly fast, yes, but it is not infinite. This seemingly simple fact profoundly reshaped our view of the cosmos. In the early 1900s, as Einstein's relativity began to take hold, physicists and astronomers found themselves in a new era of cosmic understanding. The universe was no longer a static, unchanging backdrop, but a dynamic entity, full of motion and profound mystery. Einstein's work, particularly his theories of special and general relativity, wove space and time together into a single fabric. This meant that observing distant objects wasn't just about their position, but also about their history, their journey through this woven fabric. The implications were quiet but immense. If light travels at a finite speed, then the light reaching our eyes from a distant star or galaxy left that object a long time ago. We aren't seeing it as it is asterisk now asterisk, but as it asterisk was asterisk. Consider the stars visible to the naked eye. The light from Alpha Centauri, our nearest star system, takes over 4 years to reach us. When we look at it, we are seeing it as it existed 4 years in the past. This concept is known as look-back time. The further away an object is, the longer its light has taken to travel to us, and thus, the further back in time we are seeing it. It's like a cosmic time machine with distance as its dial. Astronomers armed with increasingly powerful telescopes began to peer deeper into the night. They observed faint, fuzzy patches that were once thought to be nebulae within our own galaxy, but their true nature was far more profound. It was Edwin Hubble, working at the Mount Wilson Observatory, who made the critical measurements. He identified individual stars within these nebulae, proving they were, in fact, separate galaxies, vast island universes far beyond our own. Hubble's observations then revealed something even more astonishing. These distant galaxies were almost all moving away from us, and the further away they were, the faster they appeared to recede. The universe was not static, it was expanding. This expansion meant that light from truly distant galaxies had not only traveled for billions of years, but it had also stretched and redshifted as the space it traveled through expanded. This further deepened the look-back time. If light takes time to travel and the universe has a finite age, then there must be a limit to how far light could have traveled to reach us. A boundary not of space itself, but of what we can possibly observe. The Big Bang Theory, confirmed by the cosmic microwave background, told us the universe had a beginning approximately 13.8 billion years ago. This age sets a fundamental clock for our observations. Since light travels at a constant speed in 13.8 billion years, light can only cover a certain distance. Anything beyond that distance whose light has not yet had enough time to reach us remains unseen. This defines what we call the observable universe. It's a vast, spherical region of space centered on us, stretching out to the maximum distance from which light has had time to reach us since the Big Bang. It's crucial to understand that this boundary is not a physical wall in space. It's a horizon of information. It represents the limit of what we can *see* or *know* about the universe based on the speed of light and the age of the cosmos. Beyond this observable bubble, there is almost certainly more universe. Its light simply hasn't had enough time to travel across the vast, expanding distances and reach us here on Earth. It's still on its way, perhaps. While immense, about 93 billion light-years in diameter due to the universe's expansion during the light's journey, this observable universe is still finite. It's our cosmic bubble of perception, not necessarily the entire universe itself. Think of it like being on a ship in the middle of a vast ocean. You can only see as far as the horizon. The ocean continues beyond that horizon, but it's hidden from your view by the curvature of the Earth. Our cosmic horizon is similar, defined by light's journey through time. The cosmic microwave background, that whisper of creation, represents the earliest surface of this observable bubble. It's the light from a time when the universe was only 380,000 years old, the oldest possible light we can ever hope to detect. So what lies beyond? We can't see it, we can't measure it directly. But the universe doesn't simply stop at our observable boundary. It continues, filled with galaxies, stars, and perhaps phenomena we can only theorize about. The true size of the universe is almost certainly far, far larger than our observable bubble, perhaps even infinite. Our observable universe is just the portion of reality that has had time to communicate with us since the Big Bang. This concept of a cosmic horizon introduces a nuanced understanding of limits. It's not about a physical edge, but about the boundaries of information, dictated by the fundamental laws of physics and the age of our cosmos. But if our observable universe is just a bubble of what we can see, does the universe itself have a true edge? Or are there other, stranger horizons that might define its ultimate shape and extent? We'll begin to ponder these more elusive questions as we continue our journey. The idea of an observable universe, a bubble of what we can see, offered a new kind of boundary. But it didn't answer whether space itself had an edge. For decades, scientists had grappled with a deeper question. Was the universe simply a collection of objects moving apart, or was something more profound at play? The early 20th century brought a radical shift in perspective. It wasn't just about galaxies flying through a static void. It was about the very fabric of space, a canvas upon which the cosmic drama unfolded, and a canvas that seemed to be stretching. High atop Mount Wilson, under the clear Californian skies, Edwin Hubble meticulously peered through the Hooker telescope. He wasn't just looking at stars, he was charting the universe, measuring distances to those fuzzy spiral nebulae that dotted the night. His key was the Cepheid variable stars, pulsating beacons whose intrinsic brightness was known. By comparing their apparent brightness to their true luminosity, Hubble could calculate their immense distances, proving these nebulae were indeed galaxies far beyond our own Milky Way. But then came the next, even more astonishing discovery. By analyzing the light from these distant galaxies, Hubble and his assistant, Milton Humason, observed a consistent pattern. Their light was shifted towards the red end of the spectrum. This redshift was a Doppler effect, much like the changing pitch of a siren as it moves away. It meant these galaxies were receding from us, and critically, the further away a galaxy was, the greater its redshift, meaning it was moving away faster. This wasn't merely galaxies flying apart into an existing void. This was evidence for something far more profound. The universe itself was expanding. Space wasn't just a container, it was an active participant. Imagine dots drawn on the surface of a deflated balloon. As the balloon inflates, the dots move further apart from each other. No single dot is the center, and no dot is moving across the balloon's surface. The surface itself is stretching. Our galaxies are like those dots. They are relatively stationary within their local space, but the space between them is stretching, carrying them further apart. This is why we see redshift from all directions. It's the expansion of space itself. This model elegantly explained why every galaxy appears to be moving away from us, and why there is no apparent center to the expansion. Every point in the universe would observe the same phenomenon. Hubble's discovery, often called Hubble's law, fundamentally changed our understanding of the cosmos. The universe was not static and eternal. It was dynamic, evolving, and had a history that could be traced back to a beginning. For decades, the prevailing assumption was that this expansion, driven by the initial impetus of the Big Bang, would eventually slow down. Gravity, the great cosmic sculptor, was expected to pull galaxies back, either to a halt or even to a big crunch. But as the 20th century drew to a close, a new mystery began to unfold. Scientists, armed with more powerful telescopes and refined measurement techniques, sought to precisely measure how the expansion was slowing. Two independent research teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, embarked on a quest to measure the universe's deceleration. They used Type Ia supernova as standard candles, super bright explosions with a known luminosity. By observing these supernovae in distant galaxies, they could measure both their distance and how quickly they were receding, providing a cosmic yardstick to gauge the universe's expansion rate over time. The results, when they came in, were nothing short of astonishing. The supernovae were dimmer than expected for their measured redshift. This meant they were further away than they should have been if the expansion was slowing down. The only logical conclusion after rigorous checks and rechecks was that the universe's expansion wasn't slowing down at all. Instead of decelerating under gravity's pull, it was speeding up, accelerating into an unknown future. This was a profound shock. Gravity should pull things together, slowing expansion. For expansion to accelerate, there had to be a mysterious, repulsive force at work, pushing everything apart. Scientists called this unknown force dark energy. It's a placeholder name for something we don't yet understand, a cosmic anti-gravity that seems to be woven into the very fabric of space, growing stronger as space expands. Dark energy is now believed to constitute about 68% of the total energy density of the universe, dwarfing ordinary matter and even dark matter. It's the dominant force shaping the universe's ultimate destiny. This accelerating expansion has massive implications. If it continues indefinitely, distant galaxies will eventually recede from us faster than the speed of light, effectively disappearing beyond our observable horizon. Our future descendants, billions of years from now, might look out into a night sky that is largely empty, unaware of the vast cosmic tapestry that once surrounded us. Our observable universe would shrink to just our local group of galaxies. The discovery of dark energy transformed our understanding of the universe's expansion, shifting it from a gentle coasting to a relentless acceleration. It complicates the question of where space stops, making the very idea of a fixed boundary more elusive. If space itself is stretching and accelerating, then the concept of an edge becomes even more complex. Is the universe simply getting bigger without limit, or is this acceleration a prelude to something even stranger? This accelerating expansion introduces new kinds of cosmic horizons, boundaries not just of what we can see, but what can ever interact with us. It leads us to ponder the very nature of these elusive edges and whether they truly exist, or if the universe extends beyond our wildest imaginings, perhaps into the realm of the multiverse. The accelerating expansion of the universe, that startling discovery, introduced a new layer of complexity to our cosmic boundaries. The observable universe, our particle horizon, was defined by how far light has already traveled to reach us. But what about the future? This question became a central focus for theoretical cosmologists. If space was not only stretching but stretching at an ever-increasing rate, what would that mean for the light still on its journey towards us? The insights came not from new observations, but from patient contemplation of the existing data, combined with the profound implications of Einstein's general relativity. It was a subtle shift in perspective, from what we can see to what we will ever be able to see. This distinction was crucial, and it led to the concept of a cosmological event horizon. Imagine a distant galaxy. It emits light, and that light begins its journey across the cosmos towards us. But as the light travels, the space it traverses is expanding. If the expansion of space is accelerating, then the rate at which new space is created between the light source and us can outpace the light's own speed. It's like trying to walk towards a destination on a moving walkway that is speeding up beneath your feet. Even if you walk steadily, the walkway might carry your destination away from you faster than you can reach it. In the cosmic sense, this means there are galaxies whose light, emitted today will never reach us. The space between us and them will expand so rapidly that the light simply won't be able to bridge the ever-growing gap. This defines the cosmological event horizon, a boundary in space beyond which events can never affect us, even in the infinite future, because their light will never reach us. It's a profound difference from the particle horizon. The particle horizon is about what we can see from the past. The event horizon is about what we will ever be able to see from the present or future. The calculations confirmed a chilling realization. Due to the accelerating expansion driven by dark energy, many galaxies are already receding from us faster than the speed of light. This does not violate Einstein's theory of relativity, which states that nothing can move through space faster than light. Here, it is space itself that is stretching. Imagine a tiny ant walking on a balloon. If the balloon inflates quickly enough, even if the ant walks steadily, another ant on the opposite side might move away faster than the first ant can ever reach it. The galaxies themselves are not moving through space at superluminal speeds. Instead, the metric of space between them and us is expanding so rapidly that the distance increases faster than light can traverse it. This means that any light emitted by those galaxies will be infinitely redshifted by the time it reaches us, effectively becoming undetectable. They are, in a sense, already beyond our reach. The implications for the far future of our universe are profound. As the universe continues its accelerating expansion, more and more galaxies will cross this cosmological event horizon. Their light, already stretched and faded, will eventually disappear from our view entirely. It's as if they are falling over a cosmic waterfall, forever out of sight. In billions of years, our observable universe might shrink to encompass only our local group of galaxies, the Milky Way, Andromeda, and a few smaller companions. The rest of the cosmos, the billions of galaxies we can see today, would have receded so far and so fast that their light would no longer reach us. The night sky would become eerily empty. This isn't a physical disappearance, but an informational one. The galaxies would still exist, but they would be forever inaccessible to any form of observation or interaction from our vantage point. It paints a picture of ultimate cosmic isolation, where our future descendants might look out into a vast, empty darkness, unaware of the rich tapestry of galaxies that once filled the cosmos. This realization, born from meticulous observations and theoretical predictions, underscores the profound power of dark energy in shaping the universe's destiny. It defines a true limit to what we can ever know about the universe beyond a certain distance, a boundary that is not fixed but dynamic, ever expanding with space itself. This cosmological event horizon is perhaps the most elusive and poignant of cosmic boundaries. It's not a wall, but a fading line, a point of no return for light and information. But if these boundaries are not physical, if they are merely horizons of information, does the universe truly have an ultimate edge? Or does it extend infinitely, perhaps into realms we can only dimly perceive, like the tantalizing concept of a multiverse? The cosmological event horizon, that fading line of information, offered a profound limit to what we could ever know. But it wasn't a physical wall. It brought us to an even deeper question. What is the true, ultimate shape of space itself? Is it truly boundless, or does it curve back on itself in some grand cosmic geometry? For centuries, thinkers have pondered this. Is the universe like a flat, infinite sheet where parallel lines run forever without meeting? Or is it more akin to a vast, curved surface, perhaps like a sphere or even a saddle? In a flat universe, the rules of Euclidean geometry hold true. The angles of a triangle add up to 180 degrees, and parallel lines, if extended infinitely, would always remain parallel. This is the simplest, most intuitive shape for space. A closed universe, on the other hand, would be positively curved, like the surface of a giant sphere. In such a universe, if you set off in a straight line, you would eventually return to your starting point. Parallel lines, if extended, would eventually converge. Then there's the open universe, which would be negatively curved, resembling a saddle or a Pringle chip. In this geometry, space would be infinite, and parallel lines would diverge, spreading further apart as they extended. These three possibilities are fundamental to understanding the universe's ultimate fate and size. But how could we possibly measure the curvature of something as vast as the entire cosmos? The answer lay, once again, in the faint whispers of the cosmic microwave background. The CMB, that ancient afterglow of the Big Bang, wasn't perfectly uniform. It contained tiny variations in temperature, minuscule hot and cold spots. These were the seeds of all structure in the universe, the primordial lumps from which galaxies would eventually form. These hot and cold spots had a characteristic size when the universe was only 380,000 years old. They represented regions of slightly higher or lower density, variations that could be precisely predicted by theoretical models of the early universe. The key insight was this: the apparent angular size of these hot and cold spots in the CMB, as seen from Earth today, would reveal the universe's geometry. Space itself acts like a lens, distorting our view of these ancient features. Imagine drawing a circle of a specific size on a balloon. If the balloon is flat, the circle appears exactly as it is. But if the balloon is curved, the circle might appear larger or smaller than its true size, depending on the curvature. In a flat universe, the light from these CMB spots would travel in straight lines, unaffected by cosmic curvature. Thus, their apparent angular size would precisely match their predicted actual size at the time they emitted light. If the universe were closed and positively curved like a sphere, space would act like a magnifying lens. The light from the CMB spots would converge, making them appear larger than they truly are. Conversely, in an open, negatively curved universe, space would act like a diverging lens. The light from the CMB spots would spread out, making them appear smaller than their actual size. To measure these tiny fluctuations with enough precision, scientists needed incredibly sensitive instruments, far beyond what Penzias and Wilson had. The COBE satellite in the early 1990s gave us the first fuzzy picture, hinting at a flat universe. Then came the Wilkinson Microwave Anisotropy Probe, WMAP, in the early 2000s, and later the European Space Agency's Planck satellite. These missions were specifically designed to map the CMB with unprecedented detail and accuracy. Orbiting far from Earth's interference, WMAP and Planck meticulously scanned the entire sky for years, collecting billions of data points. They measured the temperature of the CMB at every point with precision down to millionths of a degree. The data processing was immense. Scientists had to meticulously remove foreground emissions from our own galaxy, from distant galaxies, and from instrumental noise to isolate the pristine signal of the CMB. As the maps became clearer and the statistical analysis refined, a consistent pattern emerged. The peak angular size of the hot and cold spots, the most common size they appeared to be, was exactly what was predicted for a flat universe. The evidence was overwhelming. The universe, to the limits of our observational capabilities, appeared to be spatially flat. It wasn't curved like a sphere or a saddle. It was, as far as we could tell, geometrically flat. What does flat truly mean for the universe's extent? If space is truly flat, it implies it is infinite. Just as a flat sheet of paper can extend forever, so too can a flat universe. In a flat universe, parallel lines would indeed remain parallel, even over cosmic distances. You could set off in any direction and you would never encounter an edge, nor would you ever return to your starting point. This flatness also aligns with the idea of a universe at critical density, a delicate balance where the expansion continues forever, but just barely, without ever quite stopping or collapsing back on itself. Dark energy, of course, adds another layer of complexity to this future. The universe, from the perspective of its geometry, seems to be a vast, unbounded expanse. Our observable bubble is just a small part of a potentially infinite canvas, stretching out in every direction. This discovery, born from the faint echoes of the Big Bang, solidified our understanding of the universe's overall structure. It shifted our perspective from a potentially closed, finite cosmos to one that seems to stretch on without end. But if our universe is a flat, potentially infinite expanse, does that mean it's the only expanse? Or could this vast, flat canvas be just one among many, a single bubble in a grander, more bewildering sea of realities? The idea of a multiverse, once pure speculation, now gently beckons our curiosity. Our journey through cosmic horizons and the stretching fabric of space had led us to a profound conclusion. The universe, as far as our most precise measurements could tell, appeared to be spatially flat. This suggested an infinite expanse, a canvas stretching without end. But flat doesn't necessarily mean infinite in volume. This distinction is subtle, yet crucial. A universe can be flat locally, yet still be finite overall, just as a flat sheet of paper can be folded or connected in ways that make it finite. This leads us to a fascinating, almost paradoxical idea, a universe that is boundless yet without edges. A space that you could traverse forever in a straight line without ever hitting a wall, yet eventually return to your starting point. Consider our own Earth. Its surface is a two-dimensional space. If you walk in a straight line, you will never encounter an edge or a wall. Yet the Earth's surface is undeniably finite in area. This is because the Earth's surface is curved. It curves back on itself. You can circumnavigate it, returning to your original position without ever turning back. Now, imagine this concept extended into 3 dimensions. Our universe could be finite in volume, like the Earth is finite in surface area, but still have no boundary or edge. This requires a topology, a global shape that is more complex than simple Euclidean space. It challenges our everyday intuition, which tends to equate boundless with infinite. One such shape is a hypersphere, a 3-dimensional analog of a sphere. If you traveled in a straight line in a hyperspherical universe, you would eventually loop back to where you began. Another possibility is a cosmic toroid like the surface of a donut. In such a universe, traveling straight could bring you back to your starting point, but from different directions, creating a finite yet edgeless space. These are theoretical possibilities, but how would scientists test for such a profound, hidden shape? The answer lies in looking for cosmic echoes. If the universe were finite and curved back on itself, light from distant objects would have had time to travel around the universe multiple times, reaching us from different directions. This would mean we might see the same galaxy or even the same cluster of galaxies appear in multiple places in the sky, like reflections in a cosmic hall of mirrors. The scientists search for these tiling patterns or ghost images in the distribution of galaxies across the cosmos. It's a vast, painstaking search for cosmic symmetry. Even more promising is the cosmic microwave background. If the universe were finite and looped, the patterns of hot and cold spots in the CMB might repeat across the sky. Imagine a wallpaper pattern. If the universe repeats, you might see the same arrangement of CMB fluctuations, just shifted or rotated. The search involves complex statistical analysis, looking for correlations in the CMB maps that would betray such a repeating structure. This requires immense computational power and incredibly precise data, like that gathered by the Planck satellite. The signal is faint and the universe is vast. To date, despite extensive searching, no definitive evidence of such repeating patterns has been found. The universe appears to be simply connected, meaning it doesn't loop back on itself in any detectable way. The lack of evidence doesn't entirely rule out a finite, unbounded universe, but it does place strong constraints on its size. If it is finite, it must be so large that its loops are beyond the scale of our observable universe. Any repeating patterns would be too far away or too stretched by expansion to be detected. So for now, the most consistent picture painted by our observations is that of a universe that is both spatially flat and, to the best of our knowledge, infinite in extent. It means that our observable universe, that vast bubble of information, is likely just a tiny, accessible portion of an infinitely larger cosmos. The concept of boundless without edges remains a theoretical possibility, a testament to the complex geometries that general relativity allows. But for practical purposes, our universe stretches on, seemingly without end, a canvas upon which cosmic history unfolds. Yet, if our universe is truly boundless, stretching infinitely in all directions, could it be just one of many such infinite, or even finite, universes? This leads us to the most audacious and speculative of cosmic ideas, the multiverse. The universe, our most precise measurements suggested, was spatially flat, implying an infinite expanse. Yet this elegant simplicity presented a new puzzle. If the universe started from a tiny, hot, dense point, how did it become so vast and so remarkably uniform across such immense distances? How could opposite sides of the observable universe, seemingly too far apart to have ever communicated, possess the same temperature in the cosmic microwave background? This was known as the horizon problem. Light, even at its incredible speed, hadn't had enough time since the Big Bang to travel across the entire observable universe and smooth out temperature differences. Yet, the CMB showed a stunning uniformity, a cosmic sameness that defied simple explanation. Another puzzle was the flatness problem. Our universe appears almost perfectly flat, a state that is incredibly specific. Any slight deviation from perfect flatness in the early universe would have led to a wildly different cosmos, either collapsing quickly or expanding too rapidly to form structures. It was like balancing a pencil on its tip, a delicate cosmic fine-tuning. In the late 1970s, a young physicist named Alan Guth, then at Stanford University, was wrestling with these very questions. He was exploring the physics of the very early universe, just fractions of a second after the Big Bang, looking for a mechanism that could explain these perplexing observations. Guth's background was in particle physics, and he was thinking about phase transitions, similar to how water turns into ice. He wondered if the universe underwent a similar transition, releasing enormous amounts of energy. One evening, while working on a problem related to magnetic monopoles, hypothetical particles that should have been abundant if the standard Big Bang theory was complete, he had a profound realization. What if the universe, in its earliest moments, experienced a period of unbelievably rapid exponential expansion? This was the birth of the theory of cosmic inflation. It proposed that in an unimaginably tiny fraction of a second, from about 1036 to 1032 seconds after the Big Bang, the universe expanded by a factor of at least 1026, possibly much more. This was not the slow, steady expansion we see today, but an explosive, sudden burst. To put that into perspective, imagine something the size of an atom suddenly swelling to the size of a galaxy in less time than it takes to blink. Inflation was a period of immense, almost incomprehensible growth, driven by a peculiar type of energy field. This rapid expansion, Guth realized, could elegantly solve the flatness problem. Imagine a small, wrinkled balloon. If you suddenly inflate it to an enormous size, any initial wrinkles or curves would be stretched out and smoothed, making the visible surface appear incredibly flat. Similarly, inflation would take any initial curvature of the universe and stretch it out so dramatically that, within our observable bubble, space would look perfectly flat. It's like looking at a tiny patch of the Earth's surface. It appears flat, even though the Earth is a sphere. The observations from WMAP and Planck confirming the universe's flatness provided strong observational support for this consequence of inflation. The universe, as we see it, is indeed like a perfectly smoothed-out surface. Inflation also offered a solution to the horizon problem. Before inflation, the entire observable universe was incredibly small, small enough for all its regions to be in causal contact. They could exchange energy and information, reaching a uniform temperature. Then, during inflation, this tiny, uniform patch was stretched to cosmic proportions. The regions that were once in contact were rapidly pulled apart, far beyond the reach of light, yet they retained the uniform temperature they had before the rapid stretch. So, the uniformity we see in the CMB isn't because light has had time to travel everywhere. It's because the entire observable universe originated from a region that was once small enough to be in thermal equilibrium before inflation magnified it. The theory of cosmic inflation quickly gained traction among cosmologists. It elegantly resolved several stubborn puzzles of the Big Bang model, providing a coherent picture of the universe's earliest moments and its subsequent evolution. But as scientists delved deeper into the mechanics of inflation, a more radical implication began to emerge. The very process that drives inflation might not stop uniformly across all of space. Imagine a vast, inflating sea. In some regions, inflation might turn off, allowing the energy to convert into matter and radiation, forming a universe like our own, a bubble or pocket universe. But in other regions, inflation might continue indefinitely, never quite stopping. This concept is known as eternal inflation. The inflating background would constantly spawn new bubble universes as patches of inflation came to an end. Each of these bubbles would then expand and evolve, potentially with different physical laws, different fundamental constants, or even different numbers of dimensions. Our universe, then, would simply be one such bubble. The flatness and vastness that inflation explains for our own universe could be just one instance in an infinitely larger, ever-inflating cosmic foam. The space beyond our observable bubble might not just be more of our universe, but entirely different universes. This idea of eternal inflation provides a natural, even inevitable mechanism for the existence of a multiverse. If inflation truly happened, and if it is eternal, then the universe we inhabit is not unique, but one of countless possibilities. Each bubble once formed would expand and cool, becoming its own self-contained cosmos, separated from its neighbors by vast, still inflating regions of space. These other universes would be forever beyond our reach, beyond any possible observation. The theory of inflation, born from a need to explain the uniformity and flatness of our own cosmos, thus leads us to a profound and almost unsettling conclusion. The boundaries of space might extend far beyond our single universe, into a sprawling, infinite collection of realities. Our observable universe, vast as it is, becomes a mere speck in this grander, inflationary realm. It's a humbling thought, expanding our cosmic perspective far beyond anything previously imagined. But if these bubble universes exist, what would they be like, and how could we ever hope to confirm such an audacious idea? The concept of the multiverse, once a fringe notion, now takes center stage, inviting us to ponder the most expansive and mysterious edges of reality itself. The theory of cosmic inflation, born from a need to explain the uniformity and flatness of our own cosmos, led us to a profound and almost unsettling conclusion. The boundaries of space might extend far beyond our single universe into a sprawling, infinite collection of realities. This idea, once a whispered speculation, now took center stage, the multiverse. But what exactly is a multiverse? The term itself encompasses several distinct yet interconnected theoretical concepts, each challenging our everyday intuition about reality. Scientists began to categorize these different levels of a multiverse, each arising from different physical principles. The simplest, perhaps most intuitive, idea is often called the level I multiverse. If our universe is truly infinite and spatially flat, as the CMB observations suggest, then by sheer statistical probability, everything must eventually repeat. Imagine an infinite canvas. Given enough space, every possible arrangement of particles, every possible history would eventually occur. Somewhere out there, infinitely far away, there would be another Earth, another you, reading this exact narration. This level I multiverse doesn't require new physics. It simply extends the implications of an infinite universe. It's a universe where anything that can happen will happen an infinite number of times in infinite variations, simply because there's infinite room. Then came the level Roman II multiverse, a concept arising directly from the mechanics of eternal inflation, which we explored in our last chapter. If inflation, the rapid expansion of the early universe, never truly stops everywhere, then new bubble universes are constantly being spawned. Think of it as an ever-expanding cosmic foam. Our universe is just one bubble where inflation happened to end, allowing matter and energy to form. But in other regions, inflation continues, endlessly creating new pockets of spacetime. These bubble universes wouldn't just be repeats of our own. The precise way inflation ends and the specific physical laws that emerge could vary from bubble to bubble. They could have different fundamental constants, different numbers of dimensions, or even different types of particles. This level Roman II multiverse suggests a vast cosmic landscape of possibilities, where each bubble is a distinct universe, potentially governed by its own unique set of physical rules. Our universe, then, is merely one outcome in an unimaginably vast cosmic lottery. This concept provides a compelling, if speculative, answer to why our universe seems so fine-tuned for life. If countless universes exist, it's not surprising that at least one of them would have the right conditions for stars, galaxies, and intelligent observers to emerge. Beyond these physically separated universes, another type of multiverse arises from the strange realm of quantum mechanics, the many worlds interpretation. This isn't about physical space, but about the nature of reality itself. In quantum mechanics, particles exist in a superposition of states, meaning they can be in multiple places or have multiple properties simultaneously until they are observed. It's only upon measurement that they collapse into a single, definite state. The many worlds interpretation proposed by Hugh Everett Roman III in the 1950s offers a radical alternative to this collapse. Instead of collapsing every time a quantum measurement is made, the universe itself branches. In this view, every possible outcome of a quantum event actually occurs, but in a separate, parallel universe. If an electron can spin up or spin down, then in one universe it spins up and in another it spins down. These are not physically distinct spaces, but rather diverging realities. Each branch is equally real, an alternate history where a different quantum outcome was realized. We, as observers, simply follow one particular branch. This interpretation elegantly solves some of the paradoxes of quantum mechanics, like Schrödinger's cat, by suggesting that the cat is both alive and dead, but in different non-interacting branches of reality. While profound, the many worlds interpretation is difficult to test directly, as these parallel realities are by definition inaccessible to each other. It remains a powerful philosophical framework for understanding quantum uncertainty. Finally, we encounter the cosmic landscape of string theory, a theoretical framework attempting to unify all fundamental forces. String theory suggests that the universe is made of tiny, vibrating strings, and its properties depend on how these strings vibrate and how extra dimensions are curled up. The challenge is that string theory allows for an enormous number of possible solutions to its equations, perhaps 10,500 or more. Each solution corresponds to a different way the extra dimensions can be compactified, leading to a different set of physical laws and constants. This vast array of possible solutions is what physicists call the landscape of string theory. Each valley or peak in this landscape represents a stable vacuum state, a potential universe with its own unique characteristics. If these different vacuum states can actually be realized, perhaps through the process of eternal inflation, then the cosmic landscape provides another mechanism for generating a multiverse. Our universe would simply be one of these 10,500 possibilities. This framework offers a context for the seemingly arbitrary values of fundamental constants in our universe, such as the strength of gravity or the mass of an electron. They are not uniquely determined, but are simply the values that happen to be realized in our particular corner of the landscape. The multiverse concept, whether from infinite space, eternal inflation, quantum branching, or string theory's landscape, represents a profound shift in our cosmic perspective. It suggests that our universe, vast and magnificent as it is, might be just one thread in an infinitely larger tapestry of realities. These are not just speculative tales, they are serious theoretical frameworks attempting to reconcile observations with fundamental physics. While direct evidence remains elusive for most, the implications for our understanding of where space stops are immense. If our universe is but one of many, then the concept of a singular cosmic edge dissolves into an endless, bewildering sea of realities, each potentially unique. But what does it truly mean to exist in such a boundless, perhaps infinite collection of universes? And how do we reconcile these grand theories with the very real, tangible limits of our own perception? We will ponder these final, reflective questions as our journey concludes. Our journey began with a simple yet profound question: where does space stop? We've traveled through time and across unimaginable distances, from the faint echoes of the Big Bang to the theoretical edges of existence. We first encountered a boundary not of space but of time itself in the persistent hiss of the cosmic microwave background. That ancient light, a whisper from creation, showed us the universe's earliest observable moments. Then we stretched our perception to the observable universe, a bubble defined by how far light has had time to travel since the Big Bang, a horizon of information, not a physical wall. The accelerating expansion, driven by dark energy, introduced a new kind of limit, the cosmic event horizon. A boundary beyond which light, emitted today, may never reach us, fading into an inaccessible future. We then grappled with the universe's ultimate shape, finding evidence that space is, to our best measurements, spatially flat. This suggested an infinite expanse, a canvas without end. Yet even a flat universe could be finite, a boundless space without edges, looping back on itself. The search for cosmic echoes in the CMB continues, revealing the universe to be simply connected, at least within our view. Finally, we ventured into the realm of theory, where cosmic inflation hinted at an entirely new scale of reality, the multiverse. Our universe, a single bubble in an endlessly inflating cosmic foam. From infinite repetitions to quantum branching and string theory's landscape, the multiverse concepts dissolved the idea of a singular cosmic edge into a bewildering sea of possibilities. Our journey has been a testament to human curiosity, an unwavering drive to ask the deepest questions about our place in the cosmos. From ancient stargazers charting constellations to modern scientists decoding cosmic whispers, the quest for understanding has been a continuous thread throughout history. It is a journey shaped by patience, by meticulous observation, and by the occasional breathtaking breakthrough that reshapes our entire perspective. Every faint signal, every tiny anomaly, every complex equation is a step further into the unknown, driven by the profound desire to know. Science, at its heart, is a collective endeavor. It is the shared wonder, the collaborative effort, and the open exchange of ideas that push the boundaries of our knowledge. We've seen how theories, once wild speculation, can become cornerstones of our understanding, and how unexpected noise can become the universe's oldest song. The universe, in its vastness and complexity, constantly reminds us of the limits of our current perception, but also of the boundless potential of human ingenuity. We may never find a definitive wall where space stops, because the concept itself seems to be far more nuanced than a simple boundary. Instead, we've discovered horizons of perception, of information, and of theoretical possibility, each expanding our minds in profound ways. The universe is an unfolding narrative, a grand mystery that continues to reveal new layers, each more astonishing than the last. Embracing the profound unknowns is not a sign of failure, but an invitation for future generations to continue the inquiry, to push the edges of what is known. The universe's grand, unfolding story is a source of infinite wonder, a reminder of our small yet significant place within it. It is a story that invites us to contemplate, to reflect, and to find comfort in the sheer majesty of existence. The questions may linger, the mysteries may deepen, but in that very depth lies a profound sense of peace and inspiration. We are part of this grand cosmic dance, forever learning, forever exploring, forever reaching for the stars. And as we conclude this chapter of our journey, may your own head be filled with stars, not with questions, but with a sense of calm wonder. And so, as the moon climbs high and the universe continues its silent, endless expansion, sleep well. Until our next quiet exploration, good night.